Hello, this is part 2 of solving optimization problems. If you haven't watched part 1 yet, feel free to do that. The link is in the description. But in this part, we are doing only one question, and it's very difficult, so it will take the entire video. So let's look at this. Question 3. An isosceles triangle is inscribed in a circle of radius r. Find the value of theta that maximizes the area of the triangle. And I got this from page 257, number 13, from my grade 12 calculus textbook. And in class, this was described as a very difficult question. So I will show you my solution to it so you can impress the teacher that you know how to do it. And please let me know if you have a more efficient solution, because mine definitely takes a while. So what I want to do first is look at the geometry of this diagram, because this is the only thing that they showed us in the textbook. So it really doesn't have like an obvious relationship between this angle theta and the radius. So I decided I'm going to try to figure out some geometric relationships that can relate theta to the area and to the radius. So I've drawn this dot to represent the center of the circle, and then I can recognize that the radius goes from the center all the way to the edge of the circle. So I drew the radius is going up here, and it's extending out to these two corners. And I chose to draw only those 3 lines of radius because they seem to geometrically make the most sense with this diagram. Then I've labeled this short side over here to be x, because this might come in useful during our calculation. And now I want to think about the geometry of the angles. So over here we have angle theta, but look, this triangle that I'm outlining with my mouse is actually another isosceles triangle, because these two side lengths are both the same. They're both the radius. So we can conclude that this angle here is also angle theta. So the angle in the middle must be pi minus 2 theta. In other words, 180 degrees minus 2 theta. So all the angles add up to 180 degrees within that triangle. And so now this is a straight line here, so this little angle must be 2 theta, because pi minus 2 theta plus 2 theta gives us pi, which is 180 degrees. So those relationships will help us to figure out some equations here. And now we can say that the height is this dotted line going up, so it's the total height of the triangle, and then the base is this length along the bottom of the triangle. And I would also like to note that in this situation, the radius is actually a constant and not a variable. Because you can imagine scaling this entire diagram up or down, you can make it very large or very small. It doesn't really matter what the radius is, we're still going to have the same angle to maximize the area. So in this case, you could think about the radius as just some number. For example, the radius could be 5 or the radius could be 10, but the important thing is it stays constant throughout the entire calculation. So it's not actually a variable in this situation. So let's start off with making some equations. Ultimately, we want an equation for the area in terms of the angle theta. So let's start with area equals 1/2 of base times height for the area of a triangle. So let's get some equations for the base and the height. Well, look at this. If we look at this big right triangle that I'm outlining over here, we have angle theta up there. So the tan ratio of angle theta is going to be this side length divided by this side length over here. So on the bottom, this is going to be 1/2 of the base, and then over here it's the height. So in other words, tan theta equals 1/2 of the base divided by the height. So if I rearrange to get the base by itself, we get the base is 2 times the height times tan theta. So I can sub that into the area equation, and if I simplify this a little bit, we get area equals tan theta times h squared. So this is good. Now we have it in terms of theta, but we also want to get the height in terms of angle theta, because we don't want the height in this equation. So the height is going to represent the radius plus this length x. It's okay that we have radius, because remember, the radius is just a constant, so that's fine if that's in our final equation. What we don't want is x. So let's look at how can we get rid of x. Well, in this little triangle here, we have this angle 2 theta. So we have the cosine ratio is adjacent over hypotenuse. So cos of 2 theta equals x divided by r. So x equals r times cos 2 theta. If we sub that in over here, we get the height is r plus r times cos 2 theta. And if we factor out the r, this is what we get. So now we can take this value for the height and plug it into the area equation to get this equation here. And so this represents the area in terms of angle theta. We also have the radius there, but remember that's a constant, so it doesn't matter that it's in there. So now I've just put the squared onto both the radius and this other term here to get area in terms of theta is tan theta times r squared times 1 plus cos 2 theta squared. So this is the equation that we're going to work with. So now, as usual, I want to optimize it. I need to figure out what is the derivative of this, set the derivative to 0, and solve for the value or the values of theta that will make the derivative equal 0. So let's find the derivative of this. This is quite a lot of steps, so if you want to do this in like a few smaller steps, you can. Just make sure you understand how do we get from this first one to this second step here. So since the radius squared is just a constant, it's just going to stay out front. Then here we have product rule, because we have tan theta being multiplied by this whole term here. So the derivative of tan is actually secant squared. So that's that. Then we just keep the second term the same. We add the first term times the derivative of this second term. So if we need to find the derivative of this, we use chain rule. So the 2 comes down out front. We keep this stuff the same, and subtracting 1 from the exponent just gives us exponent 1. Now we need to find the derivative of 1 plus cos 2 theta. Well, the derivative of 1 is just 0. So the derivative of cos 2 theta is negative sine 2 theta times the derivative of 2 theta, which is just 2. So as you can see, yes, that's a lot of steps. Just make sure that you understand how did we get from here to there. Now we're going to set that whole thing to 0, and in the same step, I've also done a few other things. So I've factored out the 1 plus cos 2 theta because that was actually within both of those terms. So I factored that out, and it's now out front. And over here we had 2 and negative 1 and 2, so I've just put those all together into negative 4. And now what I want to do is get everything in terms of just sine and cosine, because it's often a lot easier to solve like a messy equation like this if we just have sine and cosine rather than also having secant and tangent in there. So the secant is 1 over cos, so we can rewrite this as 1 plus cos 2 theta divided by cos squared theta. And over here, remember that the tan theta is the same thing as sine theta over cos theta. So we can also sub that in. So now everything is in terms of sine and cosine. And then finally, I'm going to subtract these two fractions. So to get a common denominator, multiply both parts of this fraction by cos theta. And then in the numerator, we have all of these adding together. And then in the denominator, we have cos squared theta. So I've just written the same thing that we just found. I'm just giving us more space. So now what we're going to try to do is find what are all the values of theta that make this equal 0. Because we have something in factored form. We have 1 plus cos 2 theta is one of the factors, and then this really big thing in the brackets is another one of the factors. So first, let's work with this. So we can say 1 plus cos 2 theta equals 0 in order to make this entire equation up here equal 0. So this is going to give us some of the solutions. So I rearranged to get that cos 2 theta must equal negative 1. And here's the graph for cos theta. So when does it equal negative 1? Well, that's when x equals pi. So in this case, we're saying that 2 theta equals pi. And so, in other words, the theta must equal pi over 2. And keep in mind, there's actually going to be infinite answers here. Because this is a sinusoidal function, it keeps repeating. So until we figure out the domain, I'm just going to stick with like the most immediate answers. But if you notice that the domain is larger, then we might need to add multiples of the period to figure out more possible values of angle theta. And now let's work with this big nasty equation over here. So we can set this factor all equal to 0. And if we multiplied both sides by cos squared theta, we end up with just saying the numerator equals 0. And so now I'm going to use trig identities. Trig identities can be really helpful to help us get rid of these two thetas and the thetas. Because it's really hard to solve an equation when some of them have theta and these other ones have 2 theta. So I know that cos 2 theta is the same thing as 2 cos squared theta minus 1. And the reason why I chose this specific identity is because the plus 1 and the minus 1 will cancel out really nicely. And then also, look, we have sine 2 theta. That's the same thing as 2 times sine theta times cos theta. So I can sub that in there as well. So the 1's cancel out. So we have 2 cos squared theta. Then here we have negative 4 times 2 is negative 8. Sine theta times sine theta is sine squared theta. And cos theta times cos theta is cos squared theta. And now if we factor out 2 cos squared theta, we get 2 cos squared theta times 1 minus 4 sine squared theta equals 0. So now what we have here are two factors again. So this out here is the first factor, and then over here is another factor. So let's set cos squared theta equal to 0. So looking at the same graph over here, we can say cos squared theta equals 0. In other words, cos theta must equal 0. So we could have pi over 2, so theta equals pi over 2, or we could have theta equals 3 pi over 2. Those would both give us an answer of 0. And now let's take a look at this. So we could say 1 minus 4 sine squared theta equals 0. And so if I rearrange for sine theta, we get sine theta is the plus or minus square root of 1/4. So sine theta is plus or minus 1/2. So if sine theta is 1/2, I've drawn the graph out here for sine theta. So look, it's 1/2 when x equals pi over 6. So theta equals pi over 6. And then we can also say theta equals 5 pi over 6. That also gives us a value of 1/2. And then the other possibility is sine theta equals negative 1/2. So looking at the graph here, we could say theta equals 7 pi over 6, or theta equals 11 pi over 6. So there's a lot of solutions here, and there actually, as I said, are infinite solutions depending on how many multiples of the period that you add. But let's try to figure out the domain to see if we actually need to find any more solutions or if we can just work with what we have here. So find the domain. Are there any restrictions on theta? I've written out the area equation from the previous slide, and I've put the same picture that they provided us from the textbook, so we can use that to figure out if there's restrictions. Well, looking at the equation, tan theta is the same thing as sine theta over cos theta. So that means this equation is undefined when cos theta equals 0. So cos theta must not equal 0 for any of these values that we've got. And also looking here, we can think logically the domain of theta must be between 0 and 90 degrees. Because you could imagine it starts at 0, it would be like a very thin line, and then it could go out and get larger until it reaches 90 degrees. But if it got any larger than that, like it wouldn't even be within this circle. So I think we can say theta is between 0 and 90 degrees. So I've written this out here. Theta is between 0 and pi over 2. Pi over 2 is 90. And then we can say cos theta must not equal 0 because it would make this equation undefined. And so notice that I've said it could equal 0, but it could not actually equal pi over 2. And that's because if we subbed in pi over 2 into cos theta, that would actually give us 0. So this means theta must not equal pi over 2, but it's okay if it equals 0 or anything in between. So this is the graph of the derivative function. So this shows all of these values of theta that we found from our calculation, and this would keep going forever in both directions. But if we narrow it down to the domain, we're looking at between 0 and pi over 2, which is this area here. So the only values of theta that were within that domain are pi over 6, and pi over 2 is just outside the domain because it's not included. So really, pi over 6 is the only valid answer out of all of these answers that fits within the domain. And now let's think, are there restrictions on other variables? Remember that we had the height, the base, and that little line representing x. Yes, it's true, these values, for example, cannot be negative. But any restrictions on them are already covered by these restrictions on theta, because this is such a narrow restriction. If you imagine subbing in any value of theta between these values into the equations with h, b, and x, you would not be outputting negative values. So everything's okay with these restrictions here. So now I'm going to check our answer by subbing all the values of theta into the area equation and see which one gives us the largest area. So when I subbed in pi over 6, I got an area of 1.30 times r squared units squared. And the reason why the r squared is still in there is because it's a constant. We don't know what the value of the radius is. So as the radius changes, that's going to affect what the area actually is. And then when I subbed in 0, I got an area of 0 units squared. And when I subbed in a number that was just slightly smaller than pi over 2, which was the other endpoint of the domain, I got an area of about 0 units squared. So we can conclude that the area of pi over 6 gives us the largest area. And as you can see in this graph, yes, this makes sense. So when we have pi over 6, this is the largest area, and the area would decrease on either side. And so the endpoints of the domain are at 0, and then over here is around pi over 2. And then after that, we'd start getting weird things like negative areas on either side of that. So to conclude, we can say, therefore, the area of the triangle is maximized when theta equals pi over 6 radians, or in other words, 30 degrees. So that's all for this video. Thank you for watching. I hope that you enjoyed this, and I will see you in the next video.